What does the brain say? In this episode, we'll explore EEG, how it records the brain's electrical activity. Imagine this. A subject sits in a lab, wearing a cap covered in electrodes, eyes fixed on a screen. First, a calm landscape plays, then suddenly, a frightening face appears. And in that instant, the EEG trace spikes. That wiggling line is the brain's voice. But how does it get there? That's what we're here to figure out. EEG, short for electroencephalogram, uses electrodes placed on the scalp to record tiny voltage changes from neurons firing in sync. Its time resolution is remarkable. It captures brain activity at the millisecond level. The trade-off is spatial resolution. Signals blur as they pass through the skull, making it hard to pinpoint exact locations. Today's question: what exactly does that waveform record? And how do we load it in MNE-Python? The core of what EEG records is the neural dipole. In the cortex, pyramidal cells are neatly arranged in columns. When millions fire together, they create a measurable electric field gradient, a dipole. That field travels through cerebrospinal fluid, skull, and scalp. The skull, however, conducts electricity poorly, attenuating the signal by several orders of magnitude. So what we measure at the scalp is the combined effect of millions of neurons firing in sync. In microvolts, 1,000 times weaker than a phone microphone. EEG frequencies fall into 5 bands. Delta, 0.5 to 4 Hz, appears during deep sleep. Theta, 4 to 8 Hz, is linked to memory encoding. Alpha, 8 to 13 Hz, is the signature of relaxed, eyes-closed states and the most studied band. Beta, 13 to 30 Hz, dominates when you're focused and alert. Gamma, above 30 Hz, is tied to higher cognition and the hardest to measure cleanly. These 5 bands are the starting point for all EEG analysis ahead. EEG has 2 main limitations. First, poor spatial resolution. Signals mix as they pass through the skull, and pinpointing activity to the millimeter level just isn't possible. fMRI is far better here. Second, susceptibility to noise. Blinking, chewing, or small movements generate artifacts far larger than the brain signal itself. Artifact removal using ICA is one of the most critical steps in EEG analysis, and we'll dedicate a full episode to it. But EEG's greatest strength is unmatched time resolution. Cognitive events like P300 unfold in hundreds of milliseconds. EEG catches all of it. Today's key takeaways. 1. EEG records microvolt level voltage changes at the scalp from millions of neurons firing in sync at up to 248 Hz. 2. Millisecond time resolution is EEG's biggest advantage. Low spatial resolution is its main limitation. 3. MNE-Python is the standard library for EEG and MEG analysis. We'll use it throughout this entire series. Next episode, loading your first EEG dataset, the raw object in MNE.